Good morning, students. Welcome back to session 5 of Hilbert spaces classes. So in the previous class, you have studied what's meant by continuous linear functionals on a Hilbert space. And the set of all continuous linear functions on a Hilbert space is denoted by H star. Okay, is denoted by H. If H is a Hilbert space, then it is denoted by H star. Okay, and also we have proved one important result, that is Rees representation theorem. Rees representation theorem for continuous linear functionals on a Hilbert space. So continuing on this, let us take up the other two results in this class. First is, in this class we first show that there is a natural one-to-one correspondence between the elements of a Hilbert space H and its dual H star. There is a natural one-to-one correspondence between the elements of a Hilbert space H and its dual H star. Okay. For this, what we have to do? First, let us define the mapping phi from H to H star by phi of any vector y is Fy, where Fy is an element of H star. It is a continuous linear functional on H. Okay, where Fy of x is equal to what? Fy of x contains, where Fy of x is inner product of x comma y. You observe this, where Fy of x is inner product of x comma y for every x belongs to H. Okay. So now, though we define phi of y is Fy, so to have a meaning for this function, okay, or the function phi is well defined only if the image element Fy lies in H star. Okay, the image element Fy must S belongs to H star. So when Fy belongs to H star, the element Fy belongs to H star if it is linear as well as it is continuous, because it must be a continuous linear functional. Let us verify that first. Okay, first we show that Fy is an element of H star. So Fy is linear. For this, let us take any two arbitrary points, say x1 and x2 belongs to H and alpha comma beta be scalars. Then Fy of alpha x1 plus beta x2 is equal to, by definition, alpha inner product of alpha x1 plus beta x2 comma y. So this is equal to alpha times inner product of x1 comma y plus beta times inner product of x2 and y. So this is equal to alpha times, what is this? Fy of x1 by definition, and beta times Fy of x2. Therefore Fy of alpha x1 plus beta x2 is alpha times into Fy of x1 plus beta times into Fy of x2. Therefore Fy is linear. First condition proved. So let us come to prove Fy is continuous. So now for each yx in H, what we have? Fy of x is inner product of x comma y. So this implies absolute value of Fy of x is certainly less than or equal to absolute value of inner product of x comma y. It is sure. So this implies what? Norm of, okay, this implies norm of x is less than or equal, this is less than or equal to norm of x into norm of y by squares inequality that you have studied in your inner product spaces class. So this is, now if I take, now norm of x is also a scalar, norm of y is also a scalar. Let us take norm of y as some scalar k. Then k is certainly non-negative, and we have absolute value of Fy of x is less than or equal to k times into norm of x. This means what? The function Fy is bounded by definition. So this implies Fy is bounded, but any bounded function is continuous, therefore implies Fy is continuous. Therefore Fy is linear as well as Fy is continuous. Therefore Fy is a functional on H, and so Fy is an element of H star. Okay, and the mapping phi is well defined now. So next we show that norm of y is same as norm of Fy. This result is very important to prove our required thing. Okay, required result, right? Now as above, yes, here for every x in H, what we have? Absolute value of Fy of x is less than or equal to norm of x into norm of y. You call this as 1. And by definition of a norm. What is norm of Fy? Norm of Fy is equal to supremum of absolute value of Fy of x such that norm of x is less than or equal to 1. Okay. Now, if norm of x is less than or equal to 1, then certainly norm of x into norm of y is less than or equal to norm of y. Therefore, if you substitute this value in 1, what do you get? From 1, this is 1, from 1, absolute value of Fy of x is less than or equal to norm y for every x with norm of x is less than or equal to 1. Now, you take a supremum of this. So, if you take a supremum of this, supremum of absolute value of Fy of x such that norm of x is less than or equal to 1 is certainly less than or equal to norm of y, because this is holds for every element, means this inequality holds for every x with norm of x is less than or equal to 1 means it holds for the supremum also. Okay, so this is, but supremum of this is nothing but what? Norm of Fy. So norm of Fy is less than or equal to norm of y. So you call this by number 2. So one way we have proved that norm of Fy is less than or equal to norm of y. So we need to prove the converse. Okay. Now if suppose y is the 0 vector, then what will happen? Norm of y is also 0. And also if y is 0, then Fy of x becomes, Fy of x is equal to what? Inner product of x comma y. So this is equal to inner product of x comma y is 0. Inner product of x comma 0 is 0. This holds for every element x in H. Means Fy of x is 0. For every x belongs to H means what? Fy is a 0 functional. Therefore Fy is a 0 functional, and norm of a 0 functional is definitely 0. Norm of a 0 functional is 0. Therefore, if y is 0, then norm of y is also 0 and norm of Fy is also 0. Therefore, norm of y is equal to norm of Fy, and the required thing proved. Okay, and the required thing will be proved if y is 0. Okay, so let y be non-zero element or y be non-zero vector in H. Now, look here. If y is a non-zero vector, what will happen? Then H is not a zero space, because H contains at least one non-zero element, which is y. Now we have norm of Fy. It is supremum of absolute value of Fy of x such that norm of x is equal to 1. Okay, this also you know by equivalent norms. So you call this as number 3. Okay. Now y is not 0 means what will happen? X, the vector x is equal to formed by y by norm of y definitely is a unit vector, because norm of x is what? Norm of y by norm of y is 1, is a unit vector. And so from 3, according to 3, what will happen? If norm of x is 1, so this is, and from 3 what will happen? Norm of Fy is definitely greater than or equal to absolute value of Fy of x. In place of x, I can take x by norm of y. Understand this? Because this is norm of Fy is the supremum of this set. Means norm of Fy is greater than or equal to each element of this set, means norm of Fy is greater than or equal to Fy of this element also. Okay. So this is greater than or equal to Fy of y by norm of y. So you apply the definition. So this is equal to inner product of y by norm of y comma y. So this is equal to 1 by norm y into s inner product of y comma y. So this is inner product of y comma y is what? Norm of y square. Norm of y square 1, norm of y cancels with this denominator, that gives norm of y. Thus norm of y, norm of Fy is greater or equal to norm of y. So you call this as 4. Now 2 says norm of y is greater than or equal to norm of Fy, and 4 says norm of Fy is greater than or equal to norm of Fy. Therefore, from 2 and 4 we conclude that norm of y is same as norm of Fy. Okay. So you take up this result as it is. Okay. Now we are going to prove the required proof. Okay. These are all the construction. These are all the preliminaries to prove the required result. So now we have defined the function what? Say phi from, look here, we have defined the function phi from h to h star by phi of y is equal to Fy, and we have shown that this mapping is well defined by showing that Fy is an element of h star, and also we have shown that norm of y is same as norm of Fi. Now we need to show this mapping is a one-to-one correspondence. One-to-one correspondence between H and H star means what? We need to show this mapping is 1-1 onto linear as well as isometry. Okay, let's prove one by one. Now let us take phi is 1-1. Phi is 1-1 means let us take y1 y2 belongs to H be arbitrary. Then phi of y1 is what? Fy1, and phi of y2 is Fy2. Okay, and we have phi of y1 is equal to phi of y2 implies what? F of y1 is equal to f of y2. This implies Fy1 of x is same as Fy2 of x for every x. This implies inner product of x comma y1 is equal to inner product of x comma y2. This implies inner product of x comma y1 minus y2 is equal to 0. This holds for every x in H. Okay. Now for every x in H means now y1 is an element of H, y2 is an element of H means y1 minus y2 is an element of H. Therefore, this condition holds for y1 minus x is equal to y1 minus y2. Therefore, I will take x as y1 minus y2. So, this implies inner product of y1 minus y2 comma y1 minus y2 is 0, taking x is equal to y1 minus y2. Now, inner product of y1 minus y2 comma y1 minus y2 is 0 means what? y1 minus y2 itself is 0. y1 minus y2 is 0 means what? y1 is equal to y2. Thus, we have taken phi of y1 is equal to phi of y2 and we have shown that y1 is equal to y2. Therefore, by definition, phi is 1-to-1. Okay. Next, phi is onto. Now, let us take f belongs to H star be arbitrary, the image space. Let f belongs to H star codomain or image space. Let f belongs to H star be arbitrary. Then, what will happen? Then, by Ree's representation theorem, there exists a unique y in H such that f of x is equal to what? Inner product of x comma y. But inner product of x comma y is nothing but fy of x according to our function. Okay. This implies f is equal to fy. F is equal to fy. Thus, phi of y is what? That's phi of y is fy. That is nothing but f. Means if f belongs to H star is arbitrary, then there exists unique y belongs to H that such that phi of y is f. Okay. Then by definition, phi is onto. Understand this? So we have taken f is an arbitrary element in H star and we have shown that there exists unique y in H such that image of that phi of y is f. Therefore, phi is onto. Next, phi is additive. Say let us take y1 y2 belongs to H. Then f of y1 plus y2 of x is what? According to our definition, inner product of x comma y1 plus y2. So this is equal to inner product of x comma y1 plus inner product of x comma y2. So inner product of x comma y1 is what? Fy1 of x plus inner product of x comma y2 means Fy2 of x means Fy1 of x plus Fy2 of x. Therefore, you can say that f of y1 plus y2 is Fy1 plus Fy2. Now you consider phi of y1 plus y2. Phi of y1 plus y2 is what? F of y1 plus y2. But f of y1 plus y2 is Fy1 plus Fy2. So f of y1 means phi of y1 plus phi of y2. Therefore, phi is linear or additive. Phi is linear. Next, phi is an isometry. Okay, phi is an isometry. For this, let us take any two elements, say y1, y2 belongs to H. Then norm of phi of y1 minus phi of y2 is what? Norm of Fy1 minus Fy2 by definition. Okay, but norm of Fy, this is equal to norm of Fy1 plus f of minus y2, because f of y2 is same as f of y2 is same as f of minus y2. Okay, it is very simple. Okay, this is equal to norm of, again this you know, norm of Fy1 plus Fy2 is f of y1 plus y2. So norm of f of y1 minus y2, f of y1 minus y2. Now I will use the result. Norm of Fy is same as norm of y, that we have proved in the beginning. So that is equal to, according to that result, what? norm of y1 minus y2. So to have this only, to have this result, we have proved in the beginning itself. Okay. So what we have, thus norm of phi y1 minus phi y2 is equal to norm of y1 minus y2. Therefore phi is an isometry. Phi is 1 1, phi is onto, phi is linear, as well as phi is isometry. Therefore by definition phi gives a norm preserving 1-to-1 correspondence between H and H star. Thus, okay, the mapping phi gives a norm preserving 1-to-1 correspondence between H and H star only. Okay. Now, so we have defined in Banach spaces also what's meant by reflexive space. Okay. So here the Hilbert space H is said to be reflexive if there exists a natural correspondence between H onto H double star. The same definition there also we have given, and we have proved the theorem also. Okay. Now the Hilbert space H is said to be reflexive if there exists a natural correspondence between H onto H double star, and this natural correspondence is an isometric isomorphism. Okay, this natural correspondence means what? It's an isometric isomorphism. Okay, here we are going to prove one important theorem. That theorem says if H is a Hilbert space, then H is reflexive. A Hilbert space is reflexive space. Okay, so for this, first in the beginning we show that each vector x in H induces a functional fx on H star. Each vector x in H induces a functional fx on H star means fx is a function from H star to f, means where fx belongs to? Fx belongs to H double star. Okay. So for each x in X, fx in S, we have a function fx on H star defined by fx of f is equal to fx of x is equal to f of x for every f belongs to H star, such that norm of fx is same as norm of x. Okay. Here observe here. Say here we have saying H star, H double star. So f belongs to H star means what? F is a function from H to C. Okay. And capital F is an element of H double star means what? Capital F is a function from H star to C. H star to C. So F acting on the elements F of H star. Okay. Understand now? So F acting on the elements F. But this f, little f, acting on the element of H, f of x. It look like f of x, it look like f of f. Okay, understand this? Now here what we are do? So we are going to prove that each vector x in H induces a functional fx on H star. Why we written, simply we can write f, but we have written fx because s, so this is a functional corresponding to the element x. Okay. So because we need to show there is a natural correspondence between H onto H double star. Okay. So fx of f is f of x, where for every f belongs to H star, and such that norm of fx is same as norm of x. In the previous theorem also, this is the theorem totally having the same step as in the previous theorem. There also we have shown norm of y is norm of fy. Okay. Here we are going to show norm of fx is same as norm of x, because so we use this while showing the isometry of the mapping. Okay, understand now? So we'll prove one by one. So this is say what's first. So now we define the mapping. T for this, define the mapping T from H to H double star defined by T of x is equal to what? T from H to H double star by T of x is equal to f. T of x is equal to fx for every x belongs to H. Defines an isometric isomorphism of H onto H double star. So this is the this is the aim of our theorem, right? So we need to show this mapping T from H to H double star is a isometric isomorphism of H onto H double star. Okay, as I said, as we show in the previous theorem also, so if I define like this, so this mapping T is well defined only when Fx is an element of H double star. When Fx is an element of H double star, if it is linear as well as it is continuous. Okay, so then only the meaning T as a meaning, or T is well defined. So first let us show Fx is a functional on H star. Okay, so first is Fx is linear. So for this, let us take any two elements f comma, let us take any two elements f and g belongs to H star be arbitrary, and take alpha and beta be scalars. Then Fx of alpha f plus beta g is by definition alpha f plus beta g of x. This is equal to alpha into f of x plus beta into g of x. So this is alpha into fx means fx of f plus beta into fx of g. Therefore fx of alpha f plus beta g is alpha into fx of f plus beta into fx of g. Therefore fx is linear. Okay, fx is linear. Now we show fx is continuous or fx is bounded. Say now for any f belongs to H star, what we have? So mod of or absolute value of fx of f is absolute value of f of x by definition we have defined. So this is certainly less than or equal to mod of f of x is certainly less than or equal to norm of f into norm of x. This we already proved in norm linear spaces. Okay, so you call this as 1. Now f is functional means what? F is continuous. F is a functional on where? Which? F is a function on H means f is a function from H to C. Now it is a function means it is continuous. Continuous means it is bounded. Now it is bounded means norm of f is less than or equal to some k. Now this is bounded means fx is also bounded because this is less than or equal to this bound. Okay, therefore yes, fx is also bounded. Now fx is bounded, fx is linear, therefore we can declare that fx is a functional on H star, or fx belongs to, in other words fx belongs to H double star. Fx belongs to H double star. Therefore the mapping what we define T of x is equal to fx is well defined mapping. Okay, now let's prove as norm of fx is same as norm of x. Same step as in the previous theorem. Okay, norm of f is equal to norm of x. We have norm of fx is equal to supremum of absolute value of fx of f such that norm of f is less than or equal to 1. So this is certainly less than or equal to supremum of, okay, because fx of f is less than or equal to norm of f into norm of x. According to that, this is less than or equal to supremum of norm of f into norm of x such that norm of f is less than or equal to 1. What about this set? Supremum of norm of f of x into norm of x such that norm of f is less than or equal to 1 means what is the supremum? So supremum is 1. When supremum of this set is when norm of f is 1. When norm of f is 1, what about this set? This becomes norm of x itself. So that is we written less than or equal to norm of x means norm of fx is less than or equal to norm of x. So you call this by number 2. Okay, now we prove the reverse inequality, that is norm of x is less than or equal to norm of fx. Okay, now to prove the reverse inequality as I proved in the last case also, so let us discuss for the case when x is 0. If x is 0, then clearly yes, norm of fx is same as norm of x, and so the required thing proved. So let x be non-zero. Okay, now if x is non-zero, then what will happen? So by corollary to Hahn-Banach theorem, what will happen? So if x is a Banach space and x0 is a non-zero vector in x, then there exists a functional f belongs to x star such that f of x0 is norm of x0 and norm of f is 1. This we have proved. So now H is a Hilbert space means it is a Banach space, so the result holds true here. So there exists a non-zero functional. Okay, so there exists a non-zero functional, say f belongs to H star such that f of x is norm of x and norm of f is 1. Okay, according to the corollary to Hahn-Banach theorem. Now norm of fx is what? Now norm of fx is supremum of mod of fx of f, where norm of f is 1 by definition of a norm. So this is equal to supremum of fx of f is what? F of x, such that norm of f is 1. So now let's come to this. What is the what? Norm of x? Norm of x is f of x, but f of x certainly less than or equal to supremum of mod of f of x, such that norm of f is equal to 1. So which is nothing but what? This is nothing but norm of f of x by definition. This is the norm of f of x. So what will happen? Norm of x is less than or equal to norm of fx. Already we have shown norm of x is greater than or equal to norm of fx. Now norm of x is less than or equal to norm of fx. You call this by 3. So from 2 and 3 we can conclude that norm of fx is same as norm of x. Okay. So this you call this by number 4. Now let's come to the actual proof of the theorem at hand. Okay. First we show T is an isometric isomorphism or natural correspondence. Okay. First T is linear. So let us take any two elements, say x comma y belongs to H and scalar alpha. Now we have f of x plus y of f is what? By definition f of x plus y. Since f is linear, this is equal to f of x plus f of y. But f of x is what? According to definition, fx of f, fy is fy of f. So this can be written as fx plus fy of f, because fx is also s, because fx is an element of h star. Okay. So fx is an element of h double star, means it's a linear functional. So it is, we have used the linearity condition here. And f of alpha x of f is what? F of alpha x, alpha into f of x, because f is also linear, fx is linear, f is linear. So this is equal to alpha into fx of f. So this can be written as alpha times fx of f. Okay, understand this? So this holds for every f belongs to h star. Therefore what you can say? Fx of x, therefore we can declare that f of, say, f of x plus y is fx plus fy, and f of alpha x is alpha times into f of x. Now let's come to S. Show T is linear. Now T of x plus y is what? F of x plus y. F of x plus y means fx plus fy. Fx is T of x plus T of y. And T of alpha x is f of alpha x. So alpha times into fx. This is equal to alpha times into T of x. Therefore T is linear. Okay, T is linear. Now let us show T is an isometry. So T is an isometry. Now, so for this, it is clear. Now norm of T of x is what? Norm of T of x is equal to norm of fx. Now norm of fx is nothing but what? Norm of x. We have proved in the beginning itself. Now norm of T of x is equal to norm of x, means T preserves norms. If T preserves norms, it is an isometry. Or in other words, we can show that norm of, say, norm of T of x minus T of y. Okay, or norm of norm of T of x minus y is equal to norm of T of x minus norm of y. So norm of T of x is what? This is norm of, again, say, fx minus fy. So this is equal to what? Norm of fx minus y. We can write like this. Norm of fx minus y is norm of x minus y. So T of x minus y is same as norm of x minus y. So therefore T is an isometry. So since it is preserves norms, we can show it is easily. Therefore T is an isometry. Now T is an linear. Next two conditions are T is 1 1 and T is odd 2. Say let us show T is 1 1. Suppose T of x is equal to T of y. If T of x is equal to T of y, what will happen? T of x minus T of y is 0. So already we have shown T is linear. This implies T of x minus y is equal to 0. So since t is a linear transformation, continuous linear transformation, this implies x minus y must be equal to 0. This implies x is equal to y. Okay, this implies x is equal to y. Therefore, what? T is 1 1. So t of x is equal to t of y implies x is equal to y. Therefore, t is 1 to 1. Now, so important part is here, t is onto. So sometimes what happens, showing t ontoness of some transformation is very simple here. That is a big task here. Okay, we show t is onto. Okay, now let us take t from h to h star be defined by t1 from h to h star be defined by t1 of x is equal to, so fx, where fx of y is inner product of y comma x for every y belongs to h. Okay, and another defined t2 from h star to h double star be defined by t2 of element of h star is fx, t2 of fx is f of fx, where f of fx of f is inner product of f comma fx. Answer now, where f of fx of f is inner product of f comma fx. This holds for every f belongs to h star, Now t1 is a mapping from h to h star and t2 is a mapping from h star to h star double star. Therefore, the composite of these two mappings is, that is say, t2 of t1. t2 of t1 is a mapping from where to where? Composition or multiplication, product. So it is a t2 of t1. t2 into t1 is a mapping from h to h double star. Okay, answer now. So t2 into t1 is a mapping from h to h double star. Okay, now clearly t1 and t2 are 1 1 and onto. Okay, clearly the mappings, we can show that these mappings t1 as well as t2 are 1 1 and onto. Just now we have shown. Okay, so now t1 and t2 are 1 1 and onto means what? t2 into t1 is also 1 1 and onto. Now t2 into t1 is also 1 1 and onto, but our aim is to show t is onto. So to show t is onto, what we do is here, we show that t2 into t1 is same as t, our t, because our t is a mapping from h to h double star and t2 into t1 is also mapping from h to h double star. So we show t2 into t1 is equal to t, t2 into t1 is equal to t. Okay, now so by definition of t, what will happen? We have t of x is equal to fx. Also t2 into t1 of x is t2 of t1 of x. So that's equal to t2 of t1 of x is fx, but t2 of fx is f of fx. Okay, so we need to show fx as well as fx are same. Okay, so let us show this. Fx of f is what? Fx of f is by definition inner product of f comma fx. So this is equal to s. So f means, say this is a function, f belongs to h star means I can take this is definitely, because there is a natural correspondence between h to h star. There is a natural correspondence between h to h star means this f is certainly corresponds to some element y belongs to h. That I return it by fy, where f is same as fy. So comma fx. So this is equal to by definition inner product of x comma y. So inner product of x comma y is what? Fy of x. Fy means, as I said, fy can be written as f itself. So f of x. That's equal to f of x is what? F of x is nothing but fx of f by our definition. F of x is fx of f. This holds for every f belongs to h star. Thus, what will happen? Look here, fx of f is same as fx, or fx is same as fx, or you write here itself. Therefore, fx is equal to fx. Now, therefore, what will happen? t2 into t1 of x is fx, that is same as fx, but that fx is same as t of x. Therefore, t2 into t1 is t. Now, t2 into t1 are 1 1 and t2 into t1 is also 1 1 and onto. Now, t2 into t1 is equal to t means what? T is, we can declare that t is onto. Now, we have shown that T is 1 1 onto linear as well as isometry. So thus T defines an isometric isomorphism of H onto H double star. If there exists an isometric isomorphism of H onto H double star, then we say that space as reflexive. So therefore the Hilbert space H is reflexive. Okay. So this is a very important result. Okay. These are the two results for this class. Thank you for listening.